All right. Hello, everyone. I'm Prasad Mani. This is my poster, and as you can see from the title, it's going to be all about convection, especially supergranular scale convection, and how convection at this scale is affected by rotation, and whether rotation is in turn affecting it. Before going into the meat of the results of my project, of my research, I would like to tell you how I study supergranulation. There are several different ways by which you can investigate convection on the sun. What I do is something called helioseismology. But before going into what helioseismology is, I want to tell you why, how and why to investigate the solar interior, especially convection, right? So how do you investigate solar interior? The only method is by helioseismology, because the sun is opaque. After a certain depth, you don't get to see what's happening inside the sun. You have to try and study phenomena on the surface of the sun, such as solar oscillations, seismic waves, to infer what must be going on in the interior. How are these waves produced? These seismic waves they are produced by turbulent convection. The vigorous near surface turbulence in the convection gives rise stochastically to these waves with random phase and amplitudes all over the surface. They penetrate in the interior. They carry the properties of the interior, such as rotation, convective flows, and magnetic fields. And these phenomena leave their mark on the seismic waves. And when you study these seismic waves, you get to see what kind of signatures have been left behind by these physics, right? So now, why do you want to study convection? There are four reasons that I managed to gather, two of which I find are the most important, which is that the small scale and the large scale dynamo, which is the small scale magnetic fluctuations all over the solar surface, and the large scale dynamo, the 11 to 22 year magnetic cycle, the solar cycle, is in fact produced by convection, or arguably thought to be produced by convection. And this gives rise to sunspots, active regions during the solar maximum. And these sunspots are stressed by convective motions, and they eventually go on to produce flares in space weather. Convection, together with meridional circulation, which is the equator to pole flow, distributes fluid angular momentum all over the convection zone, and this in turn sets up the solar differential rotation. There are two other points, but you can read them on your own. I don't want to go point by point on this 5-minute presentation. So what are these? What are the different scales of convection that's happening on the sun? Arguably, there are three scales, out of which one has been debunked as a distinct scale. The remaining two are granules and supergranules. Granules are these small scale patch of convective cells on the solar surface. The solar surface is completely covered by these granules. But when I say small, it's 1500 kilometers across and about 300 kilometers deep. The horizontal and vertical velocities. The horizontal velocities on the surface and the vertical velocities along the radial direction are comparable, and lifetime is about 5 to 10 minutes, after which new granules start forming. Granules are well studied, well understood, well reproduced in numerical simulations, whereas supergranules are a mystery. You know how big they are, how wide across they are. You know the horizontal velocities, and you can see that the vertical velocity is an order of magnitude less than the horizontal velocity. Models are not able to reproduce them faithfully. They are a complete mystery for reasons such as we don't know why supergranules prefer this length scale, or why convection prefers this length scale. This length scale is intermediate between the surface scale height and the depth of the convection zone. This thing is a puzzle, right? And why is the velocity profile of supergranules so anisotropic? Nobody knows. And it's also been found in 2003 that supergranules exhibit wave-like properties. We don't know what the driving physics behind that is. So now you would ask, why investigate this tiny detail, this single puzzling feature on the solar surface? The thing is, anything that's happening on the sun is connected to everything else on some level or the other, right? Probably the three most dynamical feature on the solar surface, that is rotation, convection, and magnetism, are intimately linked with each other. So when you study one, you have to study the other two as well. But this is easier said than done. And you have to keep in mind that if you study one and if you study another, you will leave out something else, because these three are intimately linked. Uh, in the supergranule scale, you see that there is something called magnetic network. Supergranules tend to, with the horizontal outflows, tend to advent or transport the surface magnetic fields and tend to push them out at the cell vertices, the boundaries of the supergranules where adjacent supergranules meet. And the magnetic field strength reaches about 1 kilogauss at those cell boundaries. So that's one reason why you would want to devote energy studying supergranules and how they are affected by magnetic fields. And also there's this flows that's happening on the photosphere are continuously restructuring the surface magnetic fields, and this determines the shape and the evolution of chromospheric and coronal magnetic fields, which later on tend to trigger eruptive events such as flares, CMEs, and sudden disappearance of filaments. So these are the results from my particular technique of helioseismology called normal mode coupling. I can explain the details of that technique in the video chat, but for now, just these 3 points should suffice. The first point is right there in the middle, which is that you see these clear peak in the power spectrum at about mod q, modulus q times r sun equal to 120. 120 is the typical wave number of supergranules at all latitudes. So you see that there is this radius of power at mod q equal to 120, mod qr equal to 120. Secondly, at latitude equal to 0 degree, at the equator, you see that it's only half a circle, there's this half a donut, right? You may ask why. The reason is thought to be that the supergranule waves have excess power on the prograde side, and which means power is going to accumulate eastward in the direction of rotation as compared to the west side, which is the negative qx. And this is linked to something called super rotation of supergranules, which means that supergranules rotate faster than their background. It rotates faster than 4% faster than the plasma and 2% faster than the magnetic network itself, which is strange. Nobody knows why. And as you go higher up the latitudes on both the hemispheres, you see that the power starts becoming more isotropic, which means you don't see just power on one side of the power spectrum. You see that it's a complete circle almost at 30 and 60 degrees. So the question arises whether supergranules are not rotating as fast as they are at low latitudes, and if yes, then what is the degree of influence of Coriolis force? So yeah, how are supergranules affected by rotation? And if they are affected by rotation, it's the Coriolis force that's affecting it. So we are trying to uncover the puzzle. Thank you.